Okay, everybody, welcome. What we're going to talk about today is conservation of energy, some spring stuff, and some other stuff. We're going to move on to power and other things as well. So what you should have received is a packet of notes and a packet full of worksheets. We're going to slowly work our way through those, okay? So basically, I'll give some notes, we'll write those down, and then there'll be a slide that tells you to do a particular worksheet, at which time you will do said worksheet. Feel free to please ask to pause this video at any time so that you can take down notes, solve a problem, things like that. Don't be shy. If you get through this video in a couple of days, that's great, and you get all your work done, that's really cool. You guys can watch some Mythbusters videos, you can watch some Kurzgesagt, CGP Grey, SciShow, Smarter Every Day, any science-related stuff, all right? And if you're super bored and you want to keep learning, you can email me at mchristiansen@baypath.net, and I'll put together another lesson for you. I'm just going to be posted up on the couch with my broken leg. Not broken leg, but surgeried leg. So just give me a shout and I'll put something together. But for right now, let's do some conservation of energy. So what we have so far in our arsenal of knowledge and tools and whatever in regards to energy is the formula and the idea of work, the formula of kinetic energy, the formula of gravitational potential energy, and a limited version of conservation of energy. So let's see what we can add on to this concept. So, yeah, okay. We're going to go ahead and throw in another term for our energy conservation equation. So I know a lot of you were asking when we were doing the energy bar charts what the blank space was for. This is what the blank space is for. It is for work done on the system. So if work is done on a system, then the total final energy must be the sum of all initial energies plus the work done. So if we add in work, that goes on the left-hand side of the equal sign. My stylus is not working. Hold on. It goes on the left-hand side of the equal sign. Oh, don't do this to me. So that when you add up all the work and you add up all the initial energies, okay, there we go. You add up all the work, add up all the initial energies, this number has to equal all of the final energies, that number. So that number has to equal that number. We're just including work done in our conversation about conservation of energy. So an object at rest has 425 joules of gravitational potential energy. If 200 joules of work is done on it and the object has no final velocity, then what is the new gravitational potential energy? All right, so we can use an energy bar chart to figure this out. It's very straightforward. So, oh, my stylus is, oh, there we go. All right, we start with 425 joules of gravitational potential energy. So, 425. We're going to throw a 0 in the initial kinetic energy. All right. How much work is done? 200 joules. I'll do that in blue, why not? 200 joules of work. And we're told that the object has no final velocity. So if the object has no final velocity, that means it has no final kinetic energy. All right. That means that the total energy on the left must equal the total energy on the right. We started with 425 joules of gravitational potential energy. We added in 200 joules of work. So that total is going to be 625 joules of total final potential energy. There's your answer, C. Okay. An object at rest has 425 joules of gravitational potential energy, and 200 joules of work is done on it. How much kinetic energy does it have when it is halfway between its initial height and its final height? Okay, interesting question, huh? Why don't you pause and try to figure it out, and then we'll come back to it. All right, so I'm going to assume that you've paused, worked out the problem, and come back to it. So, what we're going to do is we're going to draw an energy bar chart, and we're going to figure this out. So, energy bar chart. Okay. KEI, UI, work. KEF, UF. What do we got? Well, kinetic energy initial is going to be a big ol' 0. Nope, come on. Big ol' 0. Initial potential energy is going to be 425. And then our work, again, is 200 joules. So, let's parse this out. We need to think like a physicist in this case. So we're doing 200 joules of work on an object that already has 425 joules of gravitational potential energy. That means it's already at a certain height above the ground. That 200 joules of work is going to be put into gravitational potential energy. However, halfway between its initial and final height means that we've only added in half the work at that point. That means that we only added in 100 joules of extra gravitational potential energy. So that means that this column is only going to have 525 joules. And in order for the left-hand side to equal the right-hand side, we therefore have to have how much? 100 joules of kinetic energy final. So when we add it all up, 425 plus 200 is 625. 525 plus 100 is also 625. So we did not break physics. All right, here's a concept question for you. Same situation, start with some gravitational potential energy, add in some positive work. Does the object move up or down relative to the reference point? I want you to go ahead and pause and think about this for a second, and then we'll come back to the answer. Okay, I'm going to assume that you have thought about it and answered. The correct answer is up. It is up. We add in work, therefore we are adding gravitational potential energy. When we create more gravitational potential energy, that means we are higher, right? Since UG equals mgh, a greater gravitational potential energy must mean a greater height. So we have moved up. Okay, so we've got some simple conservation of energy problems. Oh, wait a minute. Oh, no, okay. We're good. I'm not stupid. Okay. A car of mass 150 kilograms is moving at 22 meters per second when it starts to climb a hill. The car is moving at 5 meters per second at the top of the hill, and 600 joules of work was done by the engine on the way up. And we're asked what the height of the hill is. What I would like you to do is pause, get into groups, and try to solve this problem on a big whiteboard. Okay? I don't care how long it takes you. I want you to do your very best. And then when I would say most of you think you have an answer or you get super stuck, play the video again and we'll go through the solution. So ready, set, go. All right, I'm going to assume that you have done the work and you've either come to an answer or you got stuck. That's fine. Let's go ahead and figure this out. So let's start by drawing an energy bar chart and identifying initial and final positions and solving. So our energy bar chart is going to look something like this. KEI, UI, work, KEF, UF. Okay, so if this is the case, where is the energy going to be? Well, we know that we are moving at 22 meters per second at first, so we know we're going to have KEI. We're at the bottom of the hill initially, so this is going to be a 0. And we know that we do 600 joules of work. I'm going to give that a bar at 600 joules. Now, what else? KEF. Okay, KEF. Do we have any final kinetic energy? Well, we're still moving at 5 meters per second at the top of the hill, so yes, we are going to have some final kinetic energy. I'm going to go ahead and give that a bar. We don't know the value of that yet, but we can figure it out. And then for potential energy final, we can use our physics brain to say, okay, I started with a bunch of kinetic energy, and I added in a bunch of work. I ended up with less kinetic energy than I started with, so there must be a bunch of potential energy in there, and you would end up being correct. Now let's figure out exactly how much potential energy there is. In order to do that, we need to figure out the initial kinetic energy. Okay, so kinetic energy initial is going to be 1/2 m times v initial squared, which is 1/2 of 150 times 22 squared. And that is a grand total of, calculator time, 22 squared times 150 divided by 2, 36,300 joules. Okay, so my bars are a little bit non-proportional. This should be like way up here. 36,300 joules. My KEF is 1/2 times mass times velocity final squared. That is 1/2 of 150 times 5 squared, giving us a grand total of 5 squared times 150 divided by 2, 1875 joules. 1875 joules. So this is going to be 1875. All right, so I'm going to go ahead and fix this because this should be way smaller. All right. So what are we going to do? Well, we're going to figure out the totals. So the total on the left-hand side is going to be 36,300 plus the 600 joules of work done. So that's 36,900 joules on the left-hand side. That has to equal 1,875 joules plus the potential energy final. So we subtract out 1,875, and we end up with a potential energy final of 35,025. Awesome. Now, what were we asked to find? We're asked to find the height of the hill. That means we need to use MGH. So 35,025 equals mass 150 times G 9.8 times height. So if we divide by 150 times 9.8, we end up with a height of 23.8, call it 3 meters. Alrighty. Okay. A bird drops a stone from 20 meters. How fast is it going when it reaches 1 meter above the ground? I believe I already did this problem, actually. I'll do it again anyways, but if you want to pause and go ahead and try to solve this problem, that would be superb. And then resume when you're ready to go. All right, let's go ahead and try to solve this problem. So we drop a 0.5 kilogram stone from 20 meters. How fast is it going when it reaches 1 meter above the ground? Bar chart time. Okay. KEI, UI, work, KEF, UF. Okay, so if we're dropping the stone, that means we have 0 kinetic energy initial. We do start with some potential energy initial. There is no work done. Kinetic energy final right now is a question mark, but we do know that we end up with a stone that's 1 meter above the ground, giving it much less potential energy than it started with. So if we end up with much less potential energy than we started, that means we must, by conservation of energy, have some final kinetic energy. All right? So let's figure out how much of that there is. So the potential energy initial is going to be mgh, which is 0.5 times 9.8 times 20, giving us 98 joules. Then potential energy final is also mgh, 0.5 times 9.8 times 1, giving us 4.9 joules. So the kinetic energy final has to make up the difference, which is going to be 98 minus 4.9, giving us 93.1 joules of final kinetic energy. That must equal 1/2 mv squared, where mass is 0.5. So if we divide by 1/2 times 0.5, divide by 1/2 times 0.5, we end up with a velocity squared of 372.4. Take the square root, and you end up with a velocity of 19.3, let's call it, meters per second. Okay. Now, let's talk about this. Friction causes negative work. What? Negative work? What's going on here? Oh my God, everybody panic. So, when there's friction present, we lose some energy that is present in the system. Okay, so this is one of the major problems in engineering, is losing energy by transforming it into heat due to friction. So we say, in order to account for it in our conservation of energy conservation of energy concept as negative work. And if we're drawing a bar chart, we're going to draw this as a bar below the line. Okay, so below the horizontal line, that's going to indicate a negative amount of work done on the system. It's work taken out of the system. So here we go. Let's draw a bar chart. I'm going to give you a little demo here. A system with 100 joules of initial kinetic energy. All right, let's do that. 100 joules. 600 joules of initial potential energy. Okay. 500 joules of final potential energy. And 0 joules of final kinetic energy. How much work was done in this case? Well, our total over here is only 500. Our total from here is 700. So what had to happen was there had to be negative 200 joules of work. So 200 joules of work was done to take energy away from the system. So what I'd like you to do now is I'd like you to do the energy bar charts with work practice sheet. That's the first one in your packet. Pause the video and then come back when you are done. Okay, I'm going to assume that you are done with this particular worksheet. Make sure everybody's done or close to done. and we can continue on with our learning, dear children. So, what we have so far is the conservation of energy equation. We've got potential energy being mgh. We've got kinetic energy being 1/2 mv squared. We've got work is force times distance. That is our information. Now, what is another type of potential energy? Well, we can actually store energy in a spring. Okay? Think about a dart gun. A dart gun, you pull back a plunger that pulls a spring. In order to pull that spring, you have to apply a force over a distance, right? So if you apply a force over a distance, that means that, by a force over a distance, that means you have done work on the system. That work has to go somewhere, and we say that it is stored as spring potential energy. Similarly, think about it this way. You pull back the plunger, and then you squeeze the trigger, and the dart goes. That dart gains kinetic energy, and that kinetic energy had to come from somewhere. It comes from the spring potential energy stored in the spring inside of the dart gun. All right. So mechanical energy, again, is energy due to the movement or position of an object. Again, you apply a force over a distance. This is work, and that work has to go somewhere stored as spring potential energy. Okay, pause this if you need to. All right, what we need to know about springs is, first of all, the spring constant. The symbol for the spring constant is K, and the units are newtons per meter. Newtons per meter. That means for every meter that you stretch the spring or compress the spring, it exerts a certain amount of newtons of force. The higher the spring constant, the harder it is to compress or stretch. The more force it takes to compress or stretch, right? Force, newtons per meter. There is no formula necessarily to determine the spring constant. There are tables out there depending on material and thickness of coil and number of coils and stuff like that. Usually you have to test those materials in order to figure out the spring constant. Okay, so just to check whether or not you're paying attention, which will be harder to stretch, a spring with a high spring constant or one with a low spring constant? Think and respond, look around, see who's asleep. Okay, so harder to stretch will be definitively something with a high spring constant. Okay, that's what it means. Okay, we need to also know something about springs, something called the equilibrium position. So every spring will naturally come to rest at a particular place. It has a space that it wants to return to. We're going to designate this as x equals 0, which means 0 displacement. And if the string is stretched or compressed, it will naturally want to return to its equilibrium position. That is what springs do. So here's kind of a little silly little diagram about equilibrium position. It will, when you, so let's say we have a spring and we're hanging a mass from it. Without the mass, the spring has a certain length, and then when you let it go, the mass pulls the spring down to a particular equilibrium position. When you then let's say you send the spring bouncing, it will move up and down equal distances away from the equilibrium position until it comes back to rest. All right, here's a concept check for you. A spring is hung next to a ruler. The pointer is at place 4 on the ruler. When more weight is added to the pan right here, the pointer moves down 4 places on the ruler. What is the new equilibrium position of the spring? Go ahead and think, respond. You can pause if you want. Think about it. Okay. Ready? 3, 2, 1, go. Look around. figure it out. All right, the correct answer is C, 8. So we start at 4. We move down 1, 2, 3, 4 places, and we are now at 8. All right, what are we going to do with this information? Good question. Well, we are going to use this new information to calculate something called spring potential energy. Yes, we can calculate the amount of potential energy that is stored in a spring using a formula. The symbol for spring potential energy is U subscript K, K for spring constant. Think about it like that. The units are still joules. It's still a form of energy. And the formula specifically, which is what you're all dying to know, is 1/2 kx squared, where k is the spring constant and x specifically is the distance that the spring is compressed or stretched from its equilibrium position. Okay? From its equilibrium position. Not the overall length of the spring, only the distance that it is stretched from where it wants to come to rest. I will point out, as I did with the formula for kinetic energy, that here only the x is squared, okay? So square the x first, then multiply by k, then by 1/2. Remember your PEMDAS. All right, here we go. Example time. If I compress a spring with a spring constant k equals 10 Newton per meter, a distance of 0.25 meters, how much potential energy have I stored? We have a formula. UK is 1/2 kx squared. So let's go ahead and figure k equals 10. The distance that we have compressed it is 0.25 meters. No, that's newtons per meter. How much energy? We want UK. So UK is going to be equal to 1/2 10.25 squared, giving us a grand total of 0.25 squared, no, times 0.3125 joules. Not a lot of joules there, very small amount. All right. Ready, set, moving on. Pause if you need to, as always. All right, try this on your own or with a partner. If I gain 400 joules of spring potential energy by compressing a spring 2 meters, what is the spring constant of the spring? Okay, go ahead and try this out, and we'll come back to it in a minute. Go ahead and pause. And we're back. All right, so if I have 400 joules of spring potential energy, that means I'm going to put that in as UK equals 400, and my distance of compression is 2 meters. I want to know K, the spring constant. So UK being 1/2 mv squared. Oh no, that's not right at all. Kx squared. We have 400 equals 1/2 k times 2 squared. So that becomes 4. So 1/2 k times 4 equals 400. Divide by 4. That's supposed to be a 4. We have 100 equals 1/2 k. So divide by 1/2 means multiply by 2. K is 200 newtons per meter. Okay. Now, what I would like you to do is the spring potential energy worksheet in your packet. So pause, complete that worksheet, and then resume when you have finished. Okay, I'm going to assume that you have finished that worksheet. If you have any questions on any of those problems, please email me at mchristiansen@baypath.net. I didn't solve any of these problems in this particular video, but I can give you the solution or make a quick video on, let's say everybody has a question about one of them. I can make a video quickly and put it up, and you guys can find it, and everyone will be happy. All right, let's move on. So back to conservation of energy. We can now add spring potential energy to the list of available energies in our calculations. So now, we're really getting a lot going on here, but we can now have kinetic energy, gravitational potential energy, spring potential energy, and work all in the same, well, maybe all in the same problem. Maybe not, but we just have a bunch of tools at our disposal now. So here's a question that I'm going to do out for you. A spring with K equals 50 newtons per meter is compressed 0.5 meters horizontally on a table as the diagram shows, then released so that all the stored energy is transferred into a 1 kilogram ball. How fast will that ball move the instant it leaves contact with the spring? Very interesting question here. So this is like your dart gun analogy. If I want to know how fast will my dart leave the dart gun? So let's go ahead and draw an energy bar chart for this situation. Okay, so we have KEI, UI, work, KEF, UF. All right, KEI is going to be a 0. UI, so potential energy initial, obviously we're pulling back the spring, so we are storing some potential energy initial. Work, we're going to give a 0. We're not doing any extra work. We're not pushing in addition to the spring. What you might think is, well, the spring is doing work. It's applying a force to the ball over a distance. Yes, it is. However, we have already accounted for that energy with the spring potential energy. The amount of spring potential energy that the spring holds will be exactly equal to the work that it does. So we're going to account for that energy in terms of spring potential instead of counting it as work. Okay. So we may have some kinetic energy final. And we know that once the ball leaves contact with the spring, we have used up all of our spring potential energy. That means if the left-hand side has to equal the right-hand side, we must have the same amount of kinetic energy final as we had in spring potential energy initial. That means that if we calculate UK equals 1/2 kx squared, that is 1/2, k is 50, x is 0.5 all squared, giving us a spring potential energy of 6.25 joules. Since the potential energy initial must equal the kinetic energy final, this must equal KE final. So 6.25 joules must equal 1/2 mv squared. All right. So that means that 6.25 equals 1/2 times 1 times v squared. So we divide by 1/2 times 1. We end up with 12.5 equals v squared. Take the square root of both sides, and you get a velocity of, calculator, 3.53 meters per second. Pretty cool how you can use this stuff. Okay, pause if you need to kind of process and absorb that. Because, if we're back, your turn. Try this. I would like you to get up and go to your whiteboards and try to solve this problem with a group. Take as much time as you need. Try to be speedy with it. Don't take advantage of this opportunity to goof around. When everybody is finished or super stuck, you can resume the video and I will do out the solution for you. So the same spring with 50 Newton meters of spring constant is compressed vertically this time, 0.5 meters and released onto the same 1 kilogram ball, we're asked how high the ball will go. Great, great question. So this would be like shooting a dart gun up into the air. So here we have a bar chart of the energy. I'm sorry if you don't like the bar charts. They're not always everyone's favorite. I think they can be very useful, especially when you have lots of energies going in lots of places. Use them if you want. All right, so when we pull the ball down and compress the spring, our kinetic energy is 0. Our potential energy is going to be spring potential energy. We're not doing any extra work. Now the question is, what is the final kinetic energy? It's a good question because what is a ball doing at the highest point it will ever reach if you throw it straight up? Well, it's going to have a velocity of 0. It stops just for an instant before it comes back down. That means that the final kinetic energy will be 0 at the highest point, and we are going to leave the rest of the energy in gravitational potential energy. And you might be like, what's going on? We started with a certain amount of potential energy, and the potential energy column is the same. What's up with that? Well, this is UK, spring potential energy, and this is UG, gravitational potential energy. Okay? So, our UK equals 1/2 kx squared, which again is 1/2 50 times 0.5 squared, which if I'm remembering correctly was 6.25 joules. All right. That has to equal the gravitational potential energy, which is mgh. So that 6.25 equals mass 1 times 9.8 times h. So we divide by 1 times 9.8. And we end up with a height of 6.25 divided by 9.8, 0.638 meters. And there's your answer. Okay, now I would like you to do the spring energy conservation practice worksheet. When you're done, or everybody is close to done, you can come back to the video. Actually, I'm going to end this video, and I'm going to make a part 2. I'm doing that because I only get about an hour of recording time here. So I'm going to make a part 2. When you are done with the spring energy conservation practice, you can come back and watch part 2, and I'll see you there.